And welcome to the chapter on sound. Sound is made from the vibration of large objects creating longitudinal pressure waves by vibrating at a certain frequencies, colloquially related to the term pitches. Guitars and pianos create sound by vibrating the strings at precise frequencies, drums by vibrating a thin covering, vocals by vibrating our vocal cords, and solid objects by vibrating the actual atoms of their lattice. The frequencies these will vibrate at are determined by the standing waves which can be created. This creation of a standing wave is called resonance. Every object has sympathetic frequencies which will cause a standing wave, or the atoms in the objects to vibrate at specific frequencies which are determined by the physical structure and molecular properties of the material. This can even be seen in macroscopic objects like bridges, where winds or marching feet can cause the bridge to vibrate and collapse as the wave gains amplitude. If you'll remember our discussion on standing waves will be created only when there's a relationship between the wavelength or frequency of the object and the material that it's passed through. In our example, we had the relationship that the distance or length of the rope had to be related to the wavelength by some integer number of half wavelengths. So only if the rope was one half of a wavelength, or two halves of a wavelength, or three halves of a wavelength, or so on. This caused there to be a great amount of positive interference, which is what we mean by the term resonance, when there are certain wavelengths or frequencies which cause there to be a great amount of interference, which creates waves with very, very high amplitudes compared to the initial waves which are driving them. For example, with tuning forks, a tuning fork will vibrate at a very specific frequency. It will vibrate coming together, and then the prongs coming apart and coming together and coming apart. And it will do this at a very specific frequency, which can be driven by just hitting a tuning fork on the side of something or with a mallet. If you hit a tuning fork with a pressure wave or a sound wave that is going to be at that same frequency, then that is going to cause there to be resonance. It's going to cause the tuning fork to vibrate back and forth, even if you didn't hit it physically. You only hit it with the sound of a wave from another tuning fork. This is also important in structural engineering, as you can see in this example of the Tacoma Narrows Bridge, where the frequencies or the wavelengths of winds that were coming through the Narrows happened to be exactly the wavelengths required to resonate the bridge and caused it to collapse just 4 months after its completion. Most sounds that we hear are transmitted through the air. However, any elastic substance, whether solid, liquid, gas, or plasma, can transmit sound. Elasticity is the property of a material that has changed shape in response to an applied force and then resumes its initial shape once the distorting force is removed. Steel is an elastic substance. In contrast, putty is inelastic. In elastic liquids and solids, the atoms are relatively close together, respond quickly to one another's motions, and transmit energy with little loss. Sound travels about 4 times faster in water than in air, and about 15 times faster in steel than in air. Relative to solids and liquids, air is a poor conductor of sound. You can hear the sound of a distant train more clearly if you place your ear against the rail. Similarly, you can hear the ticking of a watch set on a table beyond hearing distance if you place your ear to the table. Or click some rocks together underwater while your ear is submerged. You'll hear the clicking sound very clearly. If you've ever been swimming in the presence of motorized boats, you probably notice that you can hear the boat's motors much more clearly underwater than above water. Liquids and crystalline solids are generally excellent conductors of sound, much better than air. The speed of sound is generally greater in solids than in liquids, and greater in liquids than in gases. Sound won't travel in a vacuum because there's nothing to compress and expand. As I said, sound is a longitudinal wave where instead of the coils of a slinky being pressed together or stretched apart, it is the molecules of air. So they are compressed together at high pressures and pulled apart in rarefactions at low pressures. If you plot this versus the air pressure, what you're going to get is that same sinusoidal wave that you saw beforehand. It's just going to be that the pressure is what you're measuring instead of the height of a spring. If we watch a person at a distance chopping wood or see a faraway baseball player hitting a ball, we can easily see that the blow takes place in appreciable time before its sound reaches our ears. Likewise, thunder is heard after we see a flash of lightning. These common experiences show that sound requires a recognizable time to travel from one place to another. The speed of sound depends on wind conditions, temperature, and humidity. It does not depend on the loudness or the frequency of the sound. All sound is in the same medium travel at the same speed. The speed of sound in dry air at 0 degrees Celsius is about 330 meters per second, nearly 1,200 kilometers per hour, a little more than 1 millionth the speed of light. Water vapor in the air increases this speed slightly. Sound travels faster through warm air than cold air. This is to be expected because the faster moving molecules in warm air bump into one another more often and therefore can transmit a pulse in less time. For each degree rise in temperature above 0 degrees Celsius, the speed of sound in air increases by about 0.6 meters per second. So in air at normal room temperature of about 20 degrees Celsius, sound travels at about 340 meters per second, or using the more precise number, 343 meters per second. Sound reflects from a smooth surface the same way that light does. The angle of incidence is equal to the angle of reflection. Sometimes when sound reflects from the walls, ceiling, and floor of a room, the reflecting surfaces are too reflective and the sound becomes garbled. When sound undergoes multiple reflections and persists after the sound has ceased emitting, we hear reverberations. In addition to reflection, you also have refraction of sound, which is the fact that sound will travel uh, towards cooler air more than it will travel towards warmer air. That will cause the sound to bend from its initial path towards or away from the dog in this diagram. People can hear from about 20 hertz to 20,000 hertz at birth and gradually lose their ability to hear, especially at higher frequencies. Sound composed of frequencies higher than the range of human hearing is ultrasound, as opposed to infrasound, which is lower than the range of human frequencies. Physicians use multiple reflections and refractions of ultrasonic waves in a technique that harmlessly views the inside of the body without the use of X-rays. When ultrasound enters the body, it is reflected more strongly from the outside of an organ than from its interior, and an image of the outline of the organ is obtained. When ultrasound is incident upon a moving object, the reflected sound has a slightly different frequency. Using this Doppler effect, a physician can see the beating heart of a fetus as early as 11 weeks after conception. Sound also undergoes interference in the same way that a longitudinal wave does that we talked about in the last chapter. It's just that instead of high and low amplitudes of the wave or of displacement, it's high or low amplitudes of pressure, which is what the longitudinal wave measures. Using this property, we are able to create more complex sounds and understand a property of sounds which are called beats. If sound has two different wavelengths or frequencies, then at certain points it's going to have constructive interference, and at certain points it's going to have destructive interference. This, the frequency of this pattern as it repeats as you go from a constructive interference to another constructive interference is going to be called the beat frequency and is very useful in comprehending the idea that more complex sounds are going to be dependent on the interference patterns and the frequencies of the sounds that make them up.